Okay, everyone. Well, here, let's talk about applications of ferromagnets to finish this topic off. All right? I'm going to talk about just two applications of ferromagnets, but they're important ones. One is to make permanent magnets, which are used in things like electric motors. And the second is to make magnetic recording materials and magnetic recording equipment to make things like this. Hard disk drive. This is a 1 terabyte hard disk drive. Okay? Those are both important applications of ferromagnetics. And here, let's take a look at how they work. Hang on one second. Okay, so to talk about this, we first have to remind ourselves how ferromagnetic domains work. In a ferromagnet, although spins spontaneously align, in a macroscopic sample, or a sample above a few microns in size, we'll typically find it broken up into domains. And at zero field, the domains might be randomly aligned like this, so that their total net magnetization more or less cancels out. This turns out to be the lowest energy state. However, if we apply a magnetic field, we can get the spins in all the domains to line up. And this can happen either by growing favorably oriented domains until they dominate the whole material, or by rotating the spin direction in various domains until they line up. Here's a neat video. This was made with Kerr microscopy, which is sensitive to magnetization. And we're looking at a grain of steel and imaging the magnetization. Sorry, I want to play this again. Imaging the magnetization as the magnetic field is increased from 0. And you can see the domain walls move until this entire flake of steel is magnetized in one direction. Okay, kind of neat. If you think about that happening in a macroscopic sample, you can see how we can get to this magnetization curve for a ferromagnet. In this magnetization curve, we're going to plot magnetization, or B, M or B, which is mu naught M, as a function of the external field, which will represent with the H field here. Okay? In any event, starting from this state, if we increase the external field, we'll find the material magnetizes. The magnetization will rapidly go up. And it will go up until we reach saturation, where all the spins are aligned, much like they are in this flake of steel here. Okay? But what's interesting is that if we remove the external field now, we'll follow this curve down like this. But when we get to 0 external field, the material will remain magnetized in many cases. There's a remnant magnetization, here denoted B sub R. Okay? And that's because the magnetization produces a strong field, which is magnetizing, which is causing the spins to continue to line up in that direction. If we now increase the external field in the other direction, we go to negative values of H, the positive magnetization remains until finally we get to a point where the direction of the magnetization switches from here, from positive to negative. This occurs at the coercive field, H sub C. After that, as we continue to increase H in the negative direction, we reach saturation once again, all the spins pointing in the same direction. But then if we now remove the applied field from the negative direction, we'll see behavior that's very similar to what we just saw. Now we'll follow this curve back to 0, but we'll be left with a large remnant field, B sub R. And if we increase the field into the positive direction, it will remain magnetized until finally it switches at the coercive field again. So now, if you imagine increasing, cycling the external field from positive to negative and back again, the magnetization of the material will follow this hysteresis curve. So called because once you set the direction of magnetization and remove the external field, it exhibits hysteresis. It stays in this state until we switch it. So that at zero external field, there are actually two states that are available, fully magnetized in one direction and fully magnetized in the other direction. So that's a hysteresis curve, okay? So what can we do with a material like this? Well, one thing we can do is to make a permanent magnet, okay? So one excellent permanent magnet material is neodymium iron boron. That's what this is, although it's coated with something a little more durable and shiny on the outside. If this material is placed into a strong magnetic field, a field of a few Tesla, then we find we can reach saturation. When the field is removed, the material remains magnetized with a magnetization that's equivalent to a magnetic field at the surface of almost 1 Tesla. Okay? So now I have a 1 Tesla or almost 1 Tesla magnet that I can carry around. It's a permanent magnet. A permanent magnet should have a large magnetization, but it also should have a high coercive field so that it will remain stable no matter what happens to it. I mean, unless it's put into a field of several Tesla in the other direction. Okay, so that's a permanent magnet. Permanent magnets are important, and not just for toys like this. You probably remember that an electric motor contains electric windings in the stator, and then magnets in the rotor. And then by switching the direction of current in the stator, the outside part, we can change the direction of the forces on the rotor and get it to turn. And then if we do this right, we can get it to spin. The magnet in the rotor could be an electromagnet, but that's kind of complicated because this is rotating. And also it's complicated to make these kind of windings. Another way to do it is to use permanent magnets in the rotor. Permanent magnets based on rare earth magnets can be very compact and very powerful. So they have a high strength, they have the high power for a relatively small size. And permanent magnets, electric motors are widely used in motors for things like electric cars. Here's some data showing the prevalence of permanent magnet-based motors compared to the other type, or the motors used in electric cars, 2015, 17, 19. It's a very large fraction that use permanent motors, and it's a fraction that's kind of growing with time too. Okay, so permanent magnets are very important for that application, which itself is very important. Okay. An alternative application is for magnetic recording materials, for the recording material inside of this. So we can use magnetic materials to store information. That's because they exhibit hysteresis. If I imagine a small bit of magnetic material, it could store information because we could either leave it in this state with a positive magnetization or this state in a negative magnetization. And one of those could represent 1 and the other one could represent 0. And so this could store a bit of information. Of course, for that application, you don't want the coercive field to be very large. You'd like it to be small so that you can easily switch from one state to the other. In permalloy, for example, the coercive field is only 1/4 of a millitesla. So it's still stronger than the Earth's magnetic field, so it won't just switch randomly as you move things around, but it's a relatively small field so that we can easily switch it back and forth inside of our recording device. Okay? Magnetic recording materials are usually thin films. It's interesting to see that thin films are anisotropic, meaning that the magnetization curve for magnetization in the plane is different from that perpendicular to the plane, in this piece anyway. All right, here's an example of how this works. Here's a hard disk drive with the cover taken off. Don't do this at home. Here's the platter that contains a number of disks, perhaps, and each one has a read-write head that looks like this at the end of an arm. If we look closely at the platter, this recording material, we'll find the following. So this is a image taken with something called a magnetic force microscope. It's like an atomic force microscope, except it has a little magnet on the tip, so it's sensitive to magnetic forces. And in this image, you can see tracks. Here's one track, here's the next track, here's the next track, and each track is divided up into bits, and each bit can store one piece of information. It could be magnetized in one direction or in the opposite direction, and that would represent a 0 or a 1. Okay? And this is all very small. Note the scale. This is just 3 microns by 3 microns. And actually, this is sort of an old picture. Let me show you what it looks like now. Now it looks like this. Those two images, they're at the same scale. And now the bits are these little squares and rectangles on the surface. There are a couple of changes recently. One change is that the magnetization now is in the perpendicular direction rather than in plane. A second thing is that people have figured out how to have multiple read heads read different parts of a track. So you can have a track store more than, that at each location on a track, you can store multiple bits of information. In any event, this is very high density, okay? Here, let's take a look at how this is done. So this is the magnetic recording material. So that's one application of, another application of ferromagnets. But the devices that read and write the information to the material, those are also ferromagnetic devices. In the old days, back in the 1980s, when I was in high school, woohoo, this was done with something like this, a read-write head. In a read-write head, there's a ring-shaped head made of ferromagnetic material, and there's a coil wrapped around it. In order to write information, a current would be passed through the coil that would create a magnetic flux that would magnetize this, producing a relatively strong field at the ends of the ring where it's split here. And then that magnetic field could magnetize a bit or a section of a piece of recording material. Okay? The same ring, the same head could be used to read information too. Now, if this head is passed over one of these bits at some velocity, then the magnetic flux through the the read head will be magnetized slightly, and the magnetization will change as it passes over different bits. And the changing magnetization will induce a voltage across this coil that we can record. So that's a magnetic read head. Okay. Now this device is wonderful, but it's a little bit complicated, and it can't be miniaturized past a certain point. The way this is done now is somewhat similar, but it has some important differences too. These days, first of all, the reading function and the writing function are separated. The write head uses thin film coils, so it's much more compact. And the ferromagnetic housing creates magnetic fields that are perpendicular, like this, so that they can magnetize the film with a magnetization in the perpendicular direction. That turns out to allow them to be to make the bits smaller than they otherwise would be. Also, the read function is separated now into a separate read head. And this uses a very different technology than what we see here. Now, these are solid state devices that read the magnetization through effects like giant magnetoresistance. That was very common in the 2000s to 2010s, or now with magnetic tunnel junctions, which are completely quantum mechanical devices that are very sensitive to magnetic fields. Okay? So actually, I'd like to spend the rest of this time just talking about these last fascinating devices, magnetic tunnel junctions, okay? Because first of all, they're really cool. And I mean, gosh, tunneling, right? And secondly, they make use of many of the things that we've learned in the last chapter, last section. Okay, so magnetic tunnel junctions were invented in the 1970s, but the first practical devices came around the year 2000. And their first commercial application came in 2004 with a device from Seagate Technology. And now they're dominant. They're the dominant technology that's used to read magnetic fields. And they're based on tunneling. In this case, we measure a current that tunnels through a thin insulating gap, okay? And we're relying on a couple of things. The first is simply that if we do everything right, tunneling will preserve spin polarization. In other words, an electron that tunnels across the tunnel barrier, if it starts in a spin up state, it will end up in a spin up state as well. And if it starts in spin down, it will end up in spin down, okay? Because usually if we do things properly, there'll be nothing can happen to the electron during that process that flips its spin. The second thing to be aware of is that if we look at the free electrons inside of a ferromagnet, we'll find they're highly spin polarized. That is, if we look at the separate populations that spin up parallel to the magnetic field and spin down anti-parallel, they'll be very different. And the reason for this is essentially Pauli paramagnetism, okay? But with one important difference. In a ferromagnet, the spins don't feel the actual magnetic field, they feel the exchange field, which can be many thousands of times stronger. So in a ferromagnet, the energy spacing between the spin up and spin down bands can be very large, okay? And that produces a very dramatic population difference between the density of spin up and spin down electrons, okay? And notice that, of course, not only is the population of spin up electrons larger here, but if we look at the density of states at the Fermi energy, that's larger too. That'll be important in the next view graph. Okay, so now we can look at the following. We can contrast this case where we have two ferromagnets separated by an insulating gap, and we're looking at tunneling between them. But in this case, the fields are parallel. They're pointing in the same direction, okay? Well, then there are two processes we have to worry about. In one, spin up electrons tunnel through the barrier and end up in spin up states. There are a lot of electrons available to do this because the density of electrons in the spin up electrons is high. And there are a lot of states for them to tunnel into because the density of states at the Fermi energy is also high. So this process, the upper process here, is very heavily favored. We can also have tunneling of the spin down electrons into the spin down states on the other side, but this case is disfavored. So this is a small part of the total current. Now, that's what happens when the spins are parallel. What if they're anti-parallel? What if one material is magnetized this way, but the other one is magnetized in the opposite direction? Well, now, if we look at the spin-up electrons on the left, we have a lot of these, but because that's the disfavored population on the other side, they don't have very many states to tunnel into. So the tunneling rate, the current for this process will be suppressed relative to that. The opposite process occurs too. Spin down electrons tunnel across the barrier too. But now in this process, we still have a relatively small number of electrons that can, on the left, to tunnel across. It's true that they have a larger density of states to tunnel into. But because the current will essentially be proportional to the population on the left and the density of states on the right, it turns out that the sum of these two currents will always be larger than the sum of these two currents. So when we have parallel fields, the device will be in a low resistance state, and the current will be relatively high. Whereas when we're in the opposite state, we'll be in a high resistance state. The current will be relatively low. And the difference is large enough that it can be easily measured. In a magnetic tunnel junction device, we have these two layers, and we arrange things so that one layer is a ferromagnet with higher coercivity, and it's fixed. Its magnetization never changes. Whereas the lower layer is or the second layer, the target layer, is a layer that has a low coercivity, and it's arranged so that it's free. In other words, it can if you place it next to one of these magnetized bits, its magnetization will switch to follow the magnetization of the bit that it's in contact with. This is the free layer, okay? So as we scan this device over the disk, the direction of the free layer, magnetization in the free layer, will follow the underlying magnetization in the recording material. It'll switch from this case, the high resistance state, to this case, the low resistance state. Something like this is called a spin valve, okay? And a magnetic tunnel junction is one type of spin valve. This shows what this looks like. Here's the high resistance state. Here's the low resistance state. I think we're looking at the change from the low resistance state. And here it's 70% of the initial resistance, but it's large enough to be easily measurable. And when the device works the way it's supposed to, we're switching back and forth between this state and that state, okay? So the important thing is that magnetic tunnel junctions can be made very, very small because, well, they're a quantum device. They work on the basis of tunneling. The smaller they are, the better they work. Okay, I think we'll stop finally by I want to show you some electron microscope images of a magnetic tunnel junction. Here's the complete structure. This layer here is the magnetic tunnel junction. And if we look closely at it, we can see the following. We have two ferromagnetic layers, nickel iron and iron, and they're separated by an aluminum oxide layer. This is the scale bar in nanometers here. So the thickness of the aluminum oxide layer is only a few nanometers. So it's only a few tens of atoms thick. And in fact, you can see the atomic structure in this TEM image. All right, well, that was a couple of applications of ferromagnetism to make permanent magnets for things like electric motors. It's a very important application, one that's going to get even more important as time goes on. Rare earth metals have geopolitical significance now. And the other was to make magnetic recording materials and magnetic read and write heads for information storage. All right, well, let's wrap this up now, and I'll see you in class.